Thank you so much, everyone, for coming. And actually, we're good to go on everything? Okay, cool. Thanks so much, everyone, for coming. My name's Chris Fretz. We're here to talk about designing a slimmer vector of variance today. Okay, I was going to say the clicker was working. All right, now it is. Cool. I work at Bloomberg. I'm part of the very large Bloomberg crowd that's at this conference. Let's go ahead and get started here. So, starting out with an overview for this talk. This talk details my experience in creating a novel solution to a observed issue with memory usage that came up in production, so specifically around std vector of std variant. So the talk here starts with the motivating use case. I don't go into a huge amount of detail of exactly the motivating use case because it's internal code bases and stuff, we consider several incrementally refining designs to try to think how we might actually solve these problems. And then at the end, it presents interesting implications of this overall approach. We do benchmarks, and if we have time, I have a section on lessons learned. And so from my perspective, I implemented this data structure mostly for the fun of it. Like, the funny thing is that the original motivating use case for this actually came up for a different team that I'm not even on. At the time, I was looking for a way to get familiar with C++20 features. This sounded like a good way to go about doing that. It was actually based in a real issue that came up in production, but I mostly chose to actually go through and implement this and push it into a real implementation for the fun of it. The final presented design in this presentation is a simplified version of the actual data structure, but it should serve to illustrate the point that I'm trying to get at. For this talk, I do run a little bit close to my time. We'll see if we end up getting to the lessons learned at the end. But if people have questions, I do want them to ask them as it comes up because I think it'll help everybody with comprehension. But cool. So speaking first about the motivation. Like heterogeneous containers like vectors of variant or other ways where you can have a container that stores multiple different of a static set of types is an extremely natural way to represent data across many different paradigms. But the problem here is that like naive usage of like std vector, std variant can result in like just horrifically bad, just comically bad memory utilization if the types are of significantly disparate sizes. And if the largest types are relatively uncommon in practice. You wind up in a situation where you end up using way more memory than you actually need. And so while this is fine for examples in slide code, it looks pretty on a slide, it can lead to significant bloat in real world examples. And so just to start out here at the beginning, can anybody guess how much memory is used by this vector? So we have our combo type over here, which is a variant type of bool, int, double, string, and this big data thing. So big data it just has a 5,000 character car buffer in it. And then we have a vector of this combo type. So crucially, we don't put big data in here. We put just a bool, an int, a double, and a string. But can anybody guess how much memory they think is actually going to be used by this vector? And we're mostly interested, like, I don't care how much it takes up on the stack. We're mostly interested how much space does it take in the heap.
20,000.
Yeah, David got it. This ends up using essentially 20 kilobytes. Because the problem here is that, we're going to be seeing a lot of these diagrams throughout this talk. So let me kind of explain what we're looking at here real quick. So we have this dotted line here. Below the dotted line is the stack. So we have our vector class here that's got its size, capacity, and data. But then up top here, this is the heap up here. This is what the vector actually stores in its storage array. And so, you can see here we have our bool data, int, double, string. We have the type index with these as well, so variant can keep track of what type they are. But the problem is that you can see every single one of these things ends up being about 5,008 bytes. So we've got 5,000 for the big data, and then another 8 bytes for alignment concerns and the type index here. And so this ends up using close to 20 kilobytes, even though we literally never even used a big data. And so like the problem here is that so std variant always stores the wrap data inside of the class. And in C++, the static sizes of things need to be known at compile time. And a class always has to be the same size, a particular instantiation of it. And so since variant stores the data inside of itself, it always has to be pessimistically at least as large as the largest t, even if the largest t is never actually used. And so std vector of t assumes that all elements are of the same size. And so that brings us to our failure state. If the variant has to be as big as the largest thing that goes in, that could conceivably go into it, and the container assumes that everything is the same size, this is kind of an inevitable outcome, that we end up requiring 20 kilobytes to store a bool, an int, a double, and a string. And so assuming that a bool is a single byte, an int is 4 bytes, a double is 8 bytes, and a string is 24 bytes, the minimum conceivable memory usage for the storage array is 37 bytes. Probably in actual practice, it's not going to be possible to get that good. But at the same time, that's the minimum usage. And so what we have here is like a bloat factor of 540x. So this might seem kind of contrived, like how likely is it that we're really going to have something that's like, this out of bound from the rest of the types? But this is actually fairly close to the motivating use case that actually came up in real world code. There was a particular type that was way, way bigger than everything else by like 10x. And it was very uncommon in practice. And so we end up paying this cost all the time, even though we don't use it. And so why is vector of variant so wasteful? Vector and variant are generically composable containers. They don't really know anything about each other, and they don't cooperate with each other. And in many ways, this is one of the strengths of the STL, the fact that these things can be composed together and actually do reasonable things in most cases. But the problem in this case here is that this approach ends up leading to this significant memory bloat. And so variant is specified such that it cannot allocate, and so it has to store the data inside of itself. I think largely that's a very good thing. It does lead to the valueless by exception state and a couple other weird edge cases, but it gives us very nice performance guarantees that variant is not going to randomly allocate while your program is running. So in general, it's nice, but if you assume that all the data is the same size and you have to store all the types in situ, this is the outcome that you get. And so can we do better? This is obviously a leading question. The answer is probably yes, because we have a talk to give. But we have to be able to do better than 500 times overhead. So let's kind of think about what can we do about this. So for the first design that we want to kind of consider here, we've been talking about the fact that variant cannot allocate, and that's kind of at the heart of this issue. For the first go here, what if we just relax this requirement that variant can't allocate? Where would that actually get us? And so this is another example like we were looking at previously here. So again, this is the stack, this is the heap. So we have our std vector here as before, nothing's changed, it's exactly the same. But inside of the storage array here, we now have this my variant class instead of standard variant. And the idea here is that instead of actually storing the data directly inside of the class, we now have a pointer in each one of these things that points to somewhere else in the heap. We still have our type index here. Again, that's going to mean that each one of these things is going to end up being roughly 16 bytes, for the storage array here being 64 bytes. And then we have our 37 bytes up here as well. If we wanted to get really clever here, these are all heap allocated, so we might be able to steal some bits against these pointers and maybe kind of merge the type index and the pointer together. I'm not assuming that we're doing that in this example. And so, yeah, 64 bytes for the storage array, 37 bytes for the actual data itself in the heap. And so this new design already only uses 101 bytes. So this is already way better than our initial example here. We're now down to just 2.75x memory bloat. But the problem here is that now every single time that we push into this vector, we have to allocate from the heap for the variant that we're actually pushing in. And so we've saved a lot of memory, and our implementation remains relatively simple in this case. But we've also, we're fragmenting the heap here. We're going to be storing objects all over the place. And we've also completely demolished the performance of the data structure.
So I wonder, that's true, you have to allocate all the time, but have you tried to use PMR vector for this with memory on stack?
So actually, I did want to suggest that it is possible that you might be able to do clever stuff with allocators here. I haven't tried that specifically, but I was previously thinking if you also assume that the variant here actually takes an allocator parameter, you could potentially have an arena allocator or something like that, a stack allocator, maybe just a simple pushback allocator that just always succeeds and runs very quickly.
PMR, you can just put it on the stack.
Mm-hmm.
Right?
Yeah, yeah.
You're allocating a big chunk of memory on the start, and you're saying you're allocating from this memory. That's
Right,
it.
right. So I guess one thing that I would wonder then, like what happens when you run out of memory? Can you reallocate the region?
Yes.
Or you can actually, even on the stack?
You can even tell it to go on the heap. It will not allocate on the stop, it will go on the heap, but you can even tell it not to allocate.
Right,
So if
right.
it fails, it fails.
Okay, okay. I mean, that would actually be a really interesting direction to look into. So for this presentation here, I have not gone in that direction. My assumption here is that, so my previous thinking was that the allocator would likely end up being kind of application specific depending on the access patterns and usage that you have. I'm trying to target a generic data structure here, but that would be really interesting. I definitely want to look into that. Yeah, I'll definitely look into that. But yeah, so assuming that we don't take an approach with some kind of intelligent allocator here, we are going to have to be allocating on every single pushback, which is going to be really slow. So can we do better here? Again, leading question, I think the answer is probably yes. So candidate design number 2. So my suggestion here is that the performance overhead of allocating for every variant can't be mitigated. Would be interesting to try the PMR vector. We'll definitely look into that. But what if we kind of change directions here and try to do this a different way? So what if our vector class here was actually aware of the fact that it's storing multiple different types and that it's going to have to kind of solve this problem? Because I think crucially here, the main problem comes down to the fact that the vector and the variant don't really have any understanding of each other. And so if we take this approach, we wind up with something that looks more like this. So this vector here, the internal structure of this is the same as standard vector right now, but we have our VV vector, which is my library. Just variant vector is what it's supposed to stand for. And then up here in the storage array, we are now actually storing directly the values themselves. And so we just have our bool int double stood string, and just everything works out nicely, and we're at 37 bytes. So this design uses 37 bytes, which was our theoretical minimum. That was easy. And people say that C++ is hard. Thank you very much, everyone. That was, talk went a little bit faster than I was expecting, but yeah, obviously I'm joking here. Obviously this is not going to work. So there's tons of problems with this design at the moment right now. The first and most immediate being, how do we actually get things back out of this vector? Like at the moment right now, we just kind of have like a black hole that we can dump things into, but like that's not terribly useful. So everything is stored in one array, and each element is of potentially a different size. So like, how do we know where element n is? Like in the general case, we won't know because we don't know what's been pushed into the vector. And beyond this, each element is also potentially of a different type. And again, we're not using variant anymore, which means that we're somehow going to have to track this ourselves. Like, how do we know what type element n is? And so that brings us to candidate design number 3. So roughly the same as design number 2, but let's also add some additional storage to keep track of the types and offsets. So we can use integers to store the offsets and types. I don't literally mean int here. I just mean we can use an integer to keep track of this stuff. So the offset can be stored as the bytes from the base of the storage array, just like where does this thing actually start in the storage array. And the types can be stored as the index in the variance type list. And so to give a concrete example here from the use case we've been considering so far with the bool int double stood string, 0 would be for bool, 1 would be for int, and so we can just compute these off of the type list for the vector itself. And so this brings us to candidate design number 3. So in this case now, our vector down here is a little bit different. The start of it is the same, but we now have this offset and type pointer down here. So we now have an offset array up here and a type array over here that actually keeps track of this stuff. And so like say that we want to actually get the second like index 2 in this array. The way that we're actually going to have to do that is that the vector is going to have to consult the offset storage. It's going to see that index 2 starts at byte offset 5. It's then going to have to consult the type storage, see that this thing is a double. And then at that point, we can actually grab this thing and return it to the user. So we do have the ability now to actually keep track of what these things are and where they're located. So we can pull things back out of the vector. And so this updated design now uses 69 bytes. Crucial realization here from the first design is that we are now both more memory efficient than design number 1, and we're also significantly faster because we still have the ability to retain our amortized growth from vector. Yes?
What about alignment?
So you are ahead. Yes, we are going to get to that. There was a question that is a spoiler for coming up slides.
Don't even repeat it.
Yeah, okay. All right, sounds good. So our design now uses 69 bytes. So we're both more efficient and significantly faster. So we can now correctly discern between different types, and we also know the offsets at which things are located. And so we're good to go, right? No other problems remaining, right? And so let's write a quick test program to actually try to check this. This is probably going to feel a little bit more contrived here in Bloomberg, less so. Just to be kind of interesting here, because this is C++, it should work on every machine. Let's try running this on Solaris. And so here is our test program here. So we have our vector declared up here that's just bool int double string. We're using the same values that we've been pushing in. We then have a range for loop here that's actually going to iterate over the vector. Everything that comes out is going to be a variant. And we're going to actually visit this thing and just print out what we actually visit. And so what we should expect to see here is that this should print out 0, 1, 2.0, and 3, just because for whatever reason, cout always prints bools as zeros or ones. And so if we actually go and run this, we can see that we don't get that. What we actually end up getting here is that we print out our 0 from the first thing, and then we immediately get a bus error and a core dump and die. And so clearly there is something tragically wrong with this data structure, because this is not the result that we were hoping for here. And so, yes. Mm-hmm.
Curious, what did it do on other platforms?
Well, so actually, interestingly enough, on Linux, this does work. So when I say Linux, I actually mean x86. So on x86, this program will actually do exactly what you think it should do, and it will appear to work. But there is still undefined behavior in this program. Interestingly enough, I had a question one time about from another developer when I was giving a different version of this talk. How was I to have known this? If it would have worked on the machine I was testing it on, how was I ever supposed to figure out that I had broken the rules? And the one thing that's actually really cool here, and this was one of the ways that I was validating this data structure while I was developing it, if you instrument this program with undefined behavior sanitizer, it will immediately trap the moment that you have an unaligned access. So that is a way that you can reproduce this and test it very easily on Linux and AMD 64. But cool. Any other questions on that? All right. This gets us into the problem of memory alignment. And so welcome to the world of the compiler, or more specifically, the world that the compiler hides from you. Most code never has to think about this because the rules of the language and the compiler itself work together to abstract this problem away. And so most of the time, the compiler will just lay things out for you on the stack or in a struct such that everything is properly aligned and you never have to think about it. But the problem is that in this case here, we're actually manually laying out the memory for this vector. And so we actually get exposed to this. And so most programs don't have to think about it, but there are strict requirements that are imposed by the hardware in terms of what kinds of addresses can be legally used by different machine types. And so let's take a concrete example to illustrate what I'm talking about here. So this is a very simple just C struct here. It's just a plain old data. We just have trivial data types in here. And on the machine that I was actually doing this on, a bool would have been 1 byte, a short would have been 2 bytes, and a long would have been 8 bytes. And so 1 plus 2 is 3 plus 8 is 11. And so naively, we might expect that the size of this struct should be 11 bytes. But what we actually see here is that it's 16 bytes. And so the question is, we have 5 extra bytes that are showing up somewhere in this struct. Where is this coming from? And if we zoom into the actual layout of the struct in memory, what we end up finding out here is that we have all these padding bytes. So the bool here is only 1 byte, but there's another byte of padding between the bool and the short. And the reason for that is because the short's native alignment requirements are that it's aligned to a 16-bit or 2-byte boundary. And so this can't come directly after the bool, or we'll have the same problem we had before. And it's the same thing with the long. So this whole thing is 16 bytes wide. I was only really able to get 8 bytes on one slide. So here's the long. But what we end up seeing here is that we have another 4 whole bytes of padding here for the long. And the reason being that the long's native alignment requirements are 64 bits or 8 bytes. And so again, we can't just put it directly after this short, or we're going to get the same kind of bus errors that we were getting before. And so the compiler just does all of this for us without we having to tell it anything. And it continues to do this on the stack. Like when the compiler is statically laying out memory, it will always make sure that things are natively aligned properly. But if we look at our data structure here, the way that I'm doing this is just that, I'm allocating a primary storage array and just placement newing these things myself. And so we actually run into this problem. And so right now, there is no gap here between the bool and the int. And so if we look at the layout that we actually have here in memory, the int ends up falling on byte offset 1. And since it's a 32-bit int, it's expected to be on a 32-bit boundary or a 4-byte boundary. So it should be over here, but it's over here. And so on platforms where memory alignment is actually really a significant issue, we'll end up trapping when we actually try to access this int. Because essentially, like when we try to run this program, we try to access that int, and we're actually getting an error back from the memory bus itself that says, like, I can't do that. Like, I need to be able to, you gave me an opcode that requires 4-byte alignment, and this thing is not properly aligned. And so, as I was mentioning before, on Linux, on x86, it will just kind of fix this up for you. Like what ends up actually happening when you try to like do an unaligned read here is that the CPU will implicitly do 2 separate reads. It'll end up reading this whole 8-byte array, and then it ends up doing like, the bit shifts and fix-ups necessary to actually pull the thing out for you. But because you're doing 2 different reads, it's slower. You also run into threading concerns. Your read is no longer atomic. You can get torn writes if there are other things happening. And so it's not very good, even in the Intel case, and it's still UB either way. And so what we really need to do here is we ourselves need to inject these additional 3 padding bytes so that the whole data structure ends up properly aligned for its types. Which brings us to candidate design number 4. So it's the same as number 3, but this time around, let's make sure that our data is actually properly aligned so that we don't hit undefined behavior every time that we try to actually access this, this vector. And C++ actually has features here that can help us. So I forget if a line of was in 11 or if it was before that, but we've had a line of for a very long time. So this works like size of, essentially. You can just pass in an arbitrary type to a line of, and it will actually return to you what are the native alignments of this type. And so if I called like, a line of long, I would get back 8, saying that this has to be aligned on an 8-byte boundary. There's also a line as. So a line of can be used in any context that size of can be used, but a line as can actually be used in a declaration. And so the way that you might normally do something like this is, if you were, for some reason you needed to do this, you could declare like a character buffer on the stack or something like that. You could declare like character buffer that has size of int bytes. And the problem is that if you don't use the align as keyword there, in that case, the compiler's like, oh, this is a buffer of bytes. This doesn't have any alignment requirements. I can put it anywhere. But you can use this align as specifier to basically say like, hey, so I know this is an array of bytes, but at the same time, I need you to align it as if it's an integer, because that's what I'm actually going to be using it as. And so you can, I think align as takes both a type and also, you can also give it a number if I remember correctly. So yeah, you can use that to force a specific alignment. You can also over-align things for their type. It's pretty flexible. And then in C++17, this isn't as useful to our current use case, but we actually got the ability to do aligned allocations, which is actually really cool. The way that you used to have to do this portably was like POSIX memoline, and like be happy that you don't have to use that function. Now you can actually just do this through the global allocator in C++. You pass through this align val t where you can tell it what you need the alignment requirements to be of the pointer. And then I think that when you go to free this, you also have to call align delete. There is also an overload for delete that is aligned. But so you can actually get memory back from the heap that it conforms to specific alignment requirements. So this is super useful and helps us out a lot here. And so what we really need to get here at this point now is what we were talking about before. We need to inject these padding bytes here so that our bool and everything else in the array ends up properly aligned. And this ends up requiring like marginally more memory, but it's not really too bad. So I think that this is definitely a worthwhile trade-off. So we finally have something that actually works, and definitely will work everywhere. At this point now, our design uses 72 bytes, which is slightly worse than design number 3. But the upside is that it actually works. So that seems like a pretty good trade-off to me. And either way, it's a far cry from the 20 kilobytes of the original example. So This is a pretty good iteration here, but again, can we do better? Like, probably yes. So the first observation here is that at the moment right now, like nearly half of our total memory usage goes into the offset and type storage. And like this is pretty much pure overhead versus vector. So like our offsets over here, like vector has to somehow store the types as well, which is done in variant. But the offsets here, vector doesn't have to do any of this stuff. And so this is like, yeah, pure overhead versus the case that we're modeling. And like 32 bytes is almost half of our total requirements. And so it's really unfortunate that like we have to use basically half of our total memory just on bookkeeping for the data structure. So it has to be possible to do better than this. So the first observation here is that there will always be a static number of types that our vector is parameterized by. From one specialization to another, they may not be the same types, obviously. Like it's a generic template, you can instantiate it with any list of types, but for any individual specialization of the vector, the types will not change, will always be the same. And the other thing that we can realize here is that like it's unlikely that our vector will ever use more than a handful of types. Like, you know, in real world code, you might have a vector that uses 4 types, you might have a vector that uses 8 types, like maybe 16. You're probably not gonna have a vector that uses 64 types or 256 types. Like I mean, if somebody was trying to be problematic, you could definitely do it, but I think it's pretty unlikely. Yes?
There are limits sometimes, so the implementation cannot go to variant with 256 blows off before that.
Yeah. So the statement was that there are often limitations for an implementation where like variant itself might not be able to handle 256 types. The approach, well, actually, we'll get into the approach. My implementation does actually allow the user to do this, like please don't, but it does actually handle the case of more than 256 types. But it's unlikely that that's going to happen, and it's probably not a use case that we should really care about very much. And the thing is here is that if we know how many types we'll have to store, we can compute the minimum number of bits that are actually required to discern between those types, and we can store that type info in a bitmap, radically decreasing the storage requirements here. And so in the case of handling 4 types, in that case, you only need 2 bits to discern between 4 types. And in the case here that we've been going over thus far, where we have the 4 things in our vector, that actually means that we can store all of the type metadata in a single byte, which is actually really awesome. So that's the first observation. The second observation is that if we can put an upper bound on the size of the vector, we can compute the smallest integer type that can represent the maximum offset. And the thing is here is that like this needn't actually be a hard limit. Like if it is a hard limit, that's the best possible case. If we have like a static vector, we can treat the offset storage in the same way that we do with the types and just know that like, you know, my static vector only has 64 bytes. I'm never going to be required to, you know, to represent an offset more than 64. But we don't actually even need this to be a hard limit. If we have the ability to swap out or rebuild our index storage at runtime, we can dynamically select the smallest representation that will suffice. And so the approach that I've taken for my data structure here is basically that in the dynamic vector case, my library has both a dynamic vector and a static vector. In the dynamic vector case, it has a virtual interface that it goes through to get to the offset storage that it can use to rebuild dynamically when we go beyond you know, crucial offset boundaries. And so for candidate design number 5 here, the idea is to replace the current type storage with a bitmap that stores the types using the minimum bits possible. We also then want to replace the current offset storage with a virtual interface that will allow us to transparently rebuild or swap out the offset storage at runtime without the rest of the code base needing to be aware of this. And combining both of these approaches here should get us significantly closer to our theoretical minimum. So looking again at the actual state here, so the vector hasn't changed, but up here with our offsets now, so previously in all of the other slides, I was imagining that we were using a 32-bit integer. Now, since we know that our maximum offset here is 40, and actually the maximum offset that needs to be encoded is 16, we can actually go with a uint8 for all of these. And so obviously, a uint8 has a maximum offset storage of 255. And so if we keep pushing lots and lots and lots of more stuff in here, eventually we will trip beyond that crucial boundary. And then during the pushback itself, that's when my code would actually say like, okay, so we're about to overflow our offset storage. We need to actually rebuild this to start using 16-bit integers. And so it'll actually do this on the fly when the push happens. And with the type storage here as well, we're now using a bitmap. We only need 2 bits to be able to discern between all of these different types. And so this whole thing here with 4 types only requires a single byte for all the type storage, which is actually pretty awesome. And then this stuff over here hasn't changed. And so this optimization brings us to a grand total of 45 bytes for the full representation, which is only an overhead factor of about 20% from the theoretical minimum, which is pretty awesome. Can we still do better than this? Maybe. There's probably some things we could still do. We're probably getting to the point of diminishing returns, but there are a few additional ideas here. I mentioned before that my library also handles static vectors. At the moment right now, we've only been talking about the dynamic case because that's what vector itself is. And so it's the one that we care the most about. But if we can handle the dynamic case, the static case should be a trivial extension. Like it can use all of the same machinery, just be less complicated. And so the static vector can actually also store the contents in situ in the class. And so we can actually even avoid having to allocate anything for our offset storage, the type storage, or the actual storage for the data itself. One thing that's actually really cool here, I don't know if anybody in this room has ever had to implement a type that is conditionally movable or conditionally copyable. But the thing is that like if we want to, like say that we have a thing that goes in here that's not copyable. If vector has like a unique pointer or something that goes into it that's not copyable, the vector itself is not copyable at that point because like what would it even mean to copy it? It can't copy all of its elements. And so historically, if you've needed, like the problem is that a special lifetime function, like a copy constructor, can't be a template. It's just called out in the standard directly. And so you might want to try to sphinx out the copy constructor, but you actually can't do that prior to C++20. And so the way that this would typically be required to be done is to actually have conditional inheritance, where you actually check the types that you pass in and then have different base classes that you inherit from that declare different special lifetime functions. One thing that's really awesome in that C++20 is that you can actually put a requires clause on special lifetime functions now. And so you can actually, in your copy constructor, say that the copy constructor requires that all of the t's are copyable. Like you can do a fold expression there and have it work very nicely. And if all of your types are not copyable, your copy constructor will just sphinx out, which is actually really cool starting in C++20. There are also very natural extensions here for const_expr. So at this point now, we've gotten so much that's const_expr that you might even be able to get the dynamic case to work for const_expr. But the static case is a very natural extension for const_expr since everything is statically known. So that's one thing that we could do to kind of continue to optimize here. An additional idea here, and I don't know that I would really suggest doing this, but if you want to go for absolute minimum possible memory usage, one thing that we could do here is actually store trivially copyable types without alignment. So the idea here is that in the actual primary storage array itself, we can just store these things completely contiguously and then realign them when the user actually tries to call. So this tends to make the implementation a lot more complicated. It runs into problems for in-place mutation and all sorts of issues there. But yeah, the idea is you copy in and out and realign through the stack on access. But if we like really only care about like purely the number of bytes that we're actually using, this is something that we can conceivably do to also trim off a couple additional bytes. But cool. Awesome. So yeah, we're probably to the point of diminishing returns here, and this makes this a lot more complicated. So I don't know that I'd really suggest doing it, but you could. But awesome. So at this point now, we have a design that really significantly lowers the amount of memory usage we need. I think it also, what I've been targeting here is that it should have also like order of the same performance as vector. Like one crucial realization here is that we cannot beat vector like in terms of performance because our data structure strictly does more work than vector. And so it is always going to be slower. But the idea here is that we want to have something that is going to have the same runtime complexity for all of its functions at the very least. And so like the subscript operator, just kind of going back to the last example here, the subscript operator is going to have to take multiple levels of indirection. It's going to have to come over and read the offset and the type storage. So you're going to have to take 2 additional loads on that. With vector, it just knows that everything's the same size, so it can just compute the offset very easily. So we can't really beat that. But the point here is that it's still a constant time operation. Like it's constant time multiplied by some constant here because we're having to take multiple extra loads, but it's still a constant time operation. And for the growth strategy for this vector as well, we now need to reallocate 3 things, but we can still have amortized growth for all of these things where we exponentially allocate. And so in most cases here, we should be the same order of complexity. It's just going to be that we have some constant multiplication factor on the actual complexity. But so let's get into, at this point now, we've made a lot of changes to the way this data structure works. And so let's talk about whether or not this actually has any implications for our design. So yeah, that's kind of what I already said. But like what I was hoping for when I started out with this whole project was to get a drop-in replacement for a vector of variant that used a lot less memory. But like, do these changes have any implications for the wider API? And it's a leading question, so the answer is probably yes. The initial thing that we run into here is just challenges from the fact that we have mixed types in our vector, and vector itself doesn't expect to work that way. So many of the member functions on standard vector like implicitly assume that all of the elements in the vector are the same size. Like they don't necessarily really document that, but it's just a built-in assumption of the overall model. And so to give an example, like what does capacity mean for this data structure? Because like normally capacity would return like how many t's can I store in this vector? But the problem is that our t's aren't all the same size. And so like what do you mean? Like which t are we checking capacity for? It's the same problem for reserve. Like, you know, you would usually say like reserve 16, like I want 16 things in my vector. But again, we don't know what things you're talking about. And so reserve is also a little bit weird for this data structure. Same thing for resize. Like again, you would say resize me to 16. 16 what? It's the same problem for all of these. And so all of these functions implicitly operate on the number of elements in the vector from which the number of bytes can be directly inferred. And we can't do this. Like that's just not the way our data structure is set up. And so the approach that I've taken on this here thus far is that we have our vector here that's just the same vector we've been doing the whole time with the boolean, double, and string. I have a reserve bytes function here where you can just like directly say like, I need this vector to have 64 bytes in it. Like let me worry about what types I push in. I also have a reserve here that can take an explicit template parameter to basically say, I want to make sure that I reserve enough space for 16 strings. Resize is a little bit more interesting. So you'll notice I didn't have to explicitly tell it what type there. So resize takes a default value for the thing that you want to resize. And so if you do pass through a default value, I can actually infer what type you want to resize for based off of the default value. If you don't pass through the default value and you just want to say resize 16, you would still have to tell it that you want to do it for a string. But if you do give a default value, it actually ends up being like syntax compatible with vector.
Why did you not use a template resize to make it consistent with your reserve?
Oh, so you can specify it that way if you want to. Like it does still take a template parameter here. It's just that I can infer it off of the
function.
Exactly. Yeah, I can infer it off of the default value if you pass the default value. But if you wanted to say resize 16, you would then have to say you'd have to put the angle brackets in there and say std string, and that would just default initialize everything to a default string. You could even do it in this case. It's just redundant. But we know I have another question.
You can have also a reserve without any parameters that is the pessimistic case of the largest.
You could also do that. So the point here was that so that we make sure that we're always safe, if we don't specify something here, we could pessimistically assume that the user wants to be referring to the largest t.
Because the objective of reserve is to guarantee that there will be no allocation. So.
Yes, yeah, that's true. So if we did take that approach of pessimistically assuming the largest t, we would guarantee that we definitely have enough space for whatever you said.
You're back in the worst case.
But that's what I was about to say. Yeah, the problem with taking that approach again is that means that we're basically equivalent to vector of variant again. But you could have that as a default behavior if you wanted to make just a little bit less template noise. It's a good suggestion. Thank you. But yeah, so then we also have our capacity here, which again can be explicitly parameterized off of the type that you're interested in. And then we have a capacity bytes, which just returns like how many actual bytes do I really have right now? Another question.
What does the bracket operator return?
So that is a very good question, and we haven't gotten there yet. That is another, so the question was, what does the subscript operator return? I have a whole set of slides on that, because yeah, you're a little bit ahead of the presentation, but there are significant problems there, but cool. Any other questions on any of this stuff? Awesome, all right. So this brings us back to the implications of design. So the first challenge that we have here is that we run into semantic challenges for any functions that operate on the number of elements in the vector. Because in our particular case, it's not clear what type we're referring to when we just say this in the generic case. Are there any other implications? And again, it's a leading question. So the next implications that we run into here are the challenges of mixed alignment. And this one starts getting kind of interesting. Besides the fact that we just have multiple different types in this vector and we don't necessarily know which we're talking about, we also have challenges from mixed alignment. So we have lots of different types that are all in the same contiguous storage array, and they may have different alignment requirements. And this is actually something that I don't know that I've seen much. I don't know that I've seen many examples of mixed alignment data structures in my career, but there are some unique challenges here. So insert and erase specifically are very non-trivial to implement for this data structure. You run into all sorts of difficulties. And so consider the following code. So in this case here, we have a vector that is parameterized by just two types, a bool and a string. And as an interesting aside, that actually means that the bitmap storage for the types here would only use a single bit, which is pretty awesome. But we put just 1, 2, and 3 in here, just 3 strings. And then we immediately do the worst possible thing that we could do, and just try to push a bool directly onto the front of this vector. And so for people who've dealt with these kinds of problems before, you know why this is so problematic. But this is the worst case, so we want to kind of think about this one specifically. And then we just print out the vec1 here to show that it was actually moved. So what's the problem here? So an insertion into anywhere other than the end of the vector can actually impact downstream alignment. Generally when vector itself would do this, it has to go and move all of the stuff after it to make space for it. But we also have the additional concern of the fact that when we move those things, we don't know if we're going to end up at the right alignment boundary for them. And so the fix up here can require moving different members by different amounts. In the particular case that we have right here, where we're pushing a bool into the front, we can just add 7 padding bytes right at the beginning of the vector and everything else just works out. But in the generic case here, you actually do have to check the rest of the elements because it can have cascading effects throughout the vector. And so the memory overhead that we have to add for the alignment, the additional padding bytes that we have to inject, might actually overflow our vector. And so normally when standard vector, when you do a pushback on that, it only has to check, do I have enough bytes left for the size of t, essentially. But in our case, the size of t is bool. But we are actually going to have to end up adding 8 bytes to our vector to satisfy alignment requirements. And so knowing whether or not we're going to overflow our vector is not just as simple as looking at the size of t. We actually have to consider how many padding bytes we're going to need to add. And the thing that I ran into that is the most bizarre is that the fix-up can actually require us to shift an object in memory by less than the size of the object. And that actually happens in this exact case. And why is that so problematic and weird? So in this case here, I know that our previous slide had 3 strings in it. The strings are all the same size. They all have the same alignment requirements. They're all stored contiguously after each other. So it doesn't really matter what these 2 things are. We'll assume here that we just have a string at the beginning of the vector. And so it's 24 bytes wide. We now want to push a bool onto the front of our vector here. And because of alignment requirements, standard string has to be 8 byte aligned. We're going to have to add 7 bytes in here for padding. So we now have 8 bytes for the bool at the beginning of the thing. And so the problem is that what we actually need to do here is this. We need to move this standard string to this target location. But the problem is that this is only 8 bytes offset from where we started, and the string is 24 bytes wide. So we have 16 bytes of overlap when we're actually moving this vector, or when we're moving this string. And this gets us into really interesting places here. Was actually at a talk earlier in this conference, and I'm very happy that the speaker is actually here, called An Incomplete Guide to Object Lifetimes. And one thing that I'm wondering about here is that, so when we actually do this move, so here's my concern. The way that I fix this problem is that if we actually wind up in the overlapping case, I actually move the string through a temporary instance on the stack to make sure that we don't end up actually corrupting memory here. But what I've always wondered about is that, say that this thing that we're moving is not a standard string, because a standard string will conceivably produce observable side effects from its actual move operator. If we have just a standard plain old data C struct in here, and we actually try to do this, what I've always wondered about is, can the compiler decide to elide the temporary? Because if it does, it will completely break my logic. The way that I've set this up at the moment is that the function that handles this is called move overlapping pointers. I pass that through as a 2 pointers to car, essentially, and I use placement new to do the moves, under the hope that that will encourage the compiler to realize that these 2 pointers might alias, and that it can't actually elide that temporary. But I don't actually know what's guaranteed by the standard here. And I think it's genuinely an interesting case. I'm wondering if anybody in the audience happens to know. And if not, that's fine. I didn't get an answer when I tried to ask at the C++ guild internally in Bloomberg. I actually got conflicting answers on this one. But the approach that I take here is that, the function that does the move takes them by character pointers to try to make the compiler think that the storage spaces may overlap. But yeah, so this is the ultimate state that we want to get into here. And so for the challenges of mixed alignment, during an insert, we have to walk the vector and recompute the alignment boundaries as we go, reallocating at the end if necessary. So we have to walk the whole way to the end to figure out how many padding bytes are we going to have to add. We can then walk backwards and move the objects forward to make space for the insertion. That's pretty close to how vector itself actually works. And if a move would result in overlapping pointers, we move through a temporary instance on the stack to try to avoid accidentally corrupting the object. Because the fear here at the end of the day is that if we don't do that, while we're actually copying here, we're going to be mutating the object. So we're just going to get totally undefined results out of that.
Just a small thing that you can add to make the compiler not to remove or optimize out your temporary is to make it volatile. It's one of the things that volatile is still good for.
That's actually really interesting, yeah.
It will not cache it, it will not remove it because it has side effects.
So the only thing that's a really interesting idea. The only thing I would be concerned about there is that when I'm doing this, so this is going to be a user-controlled, user-defined type. A lot of users don't consider volatile when they write their classes. So the only thing that I wonder about there is whether or not we might end up winding up in a situation where we don't actually call what the user expects. If you have a normal move constructor that just takes t ref, you would need t volatile ref, right? Or
that's not a valid thinking.
Yeah. So does it just...
You cannot do that with parameters. You can do it with pointers. You can declare a pointer that is volatile. You can declare something on the stack. Just tells the compiler, please don't optimize this out.
So that would still use the normal move constructor?
If inside the move constructor you will declare something that is volatile for yourself. Yeah.
Okay. Yeah, well, that's a very interesting idea. I would want to do some testing with that just to see how it behaves, but that is a really cool idea. So the idea here basically is that when we declare the temporary on the stack, we declare it volatile so that the compiler can't elide those reads and writes. But we had another question.
On the same thread.
On the same
thread.
Yes.
That's the most important part.
Yes. And we had another question.
Could you be in a situation in which, because of the padding, when you insert an element, you don't have to move all the rest of the elements?
Yes, you can have that happen. That is very true. So the question was, because of the fact that we're injecting padding bytes, can we wind up in a situation where when we try to insert, we just have padding bytes that are free and we don't have to move anything? That absolutely can happen. And if we took this example here, so if we ran this exact same insert a second time, this would not require us to move anything. We could actually run this insert 7 more times before we would actually have to insert anything. And that is how this works.
Or even you might not need to move all the rest of the elements, but let's say 10.
Correct.
You accumulate, push.
I think that, yes, that is definitely true. So I've seen personally that, so this is one thing that I've wondered. Do you actually really have to compute alignment to the whole end of the data structure? Or can you just say, once I get to a maximum alignment boundary, I know that the rest of the data structure doesn't have to...
Once your padding takes care of it, it sounds like you could terminate all your alignment and insertion.
Well, so in this case, there's only one thing that we have to do here. Actually, I realized the thing I was going to try to jump back to is like 30 slides back, so I'm not going to do it. But I do know that there are cases where it doesn't just happen once. Like it causes a cascading effect where other things end up misaligned. Now, what I think probably is
If you
true.
had a bool at the beginning, right, and then you want to push another bool in, you see you have the padding, you put it in. You don't need to realign or even
Correct.
calculate the rest of the realignment.
Correct. Yeah, and in that case, I wouldn't. That is how this
So
works.
you terminate early. If you anywhere you found that the push
Mm-hmm.
had your padding, stop there and then work backwards.
Yeah. Yeah, you definitely can do that. My main question is just like, yeah, if you don't have those padding bytes there, like say that for this one here, we actually do have to move things. Do we actually have to scan the rest of the vector? Or can we just say once we make it to the maximum alignment requirement for this vector that we just don't look at anything beyond
Common
that?
sense wise, yes.
Yeah,
Check.
there might be some weird case. Yeah, exactly.
Check.
But cool. Any other questions on any of this? Cool.
Seems
Oh.
that insert can be awfully inefficient.
Yeah. I mean, that is definitely true. So, I mean, that is one thing that I kind of think about here generally is that inserting onto the front for a vector in general is like not really something that most people will be doing if you care about performance. But yeah, ours does definitely have additional overhead on the fact that like I have to spend all this time like computing the alignment and looking at things. And potentially I have to do double moves for some things to actually get it to work properly. So it is definitely more expensive than vector. I think again, it's not like it's a constant factor more expensive than vector, but it is definitely more expensive than vector. But this is definitely an expensive thing to do even in the normal vector case. But another question.
How deeply did you look into the trivially relocatable thing? Because it seems like that would simplify a lot of this.
I haven't actually. It's what would you suggest there?
Well, basically, trivially relocatable
Does that mean like you can just like mem move it
means
essentially?
memcopy produces a valid object in the destination.
Okay.
And that way you don't have to worry about the padding. The only thing you have to make sure you don't do is leak out a reference to something.
Right. Okay. Yeah, I'll definitely take a look at that. Yeah, and so at the moment right now in the actual real implementation of this, I have a couple different branches of this. If the type itself is trivially copyable, that's the trait that I use. I don't go off of trivially relocatable. But if it's trivially copyable, then I just use memcopy. If the regions are overlapping, then I use memmove. But I do just use those basic functions. It's only in the cases where the thing is not trivially copyable that I go through all of this additional machinery. But another question.
Since we're talking about insert, I think Alex Stepanov in one of the A9 Amazon lectures, he introduces a data structure that's called state. Something like this.
Oh, is it really? Oh,
Yeah,
that's
I
really
think it's
cool.
the same thing.
That's awesome.
And I'm sure it doesn't have insert because it's on tape.
Right, yeah.
But besides that, I don't know all the differences. But
That's really, we'll definitely
Yeah.
look into that. That's fascinating. There's that old saying about like nothing new is under the sun or whatever. Like everybody's done everything before. But that is really cool. I'll definitely look into
I
that.
think it's an A9 GitHub repository. The code. I think it never ends explaining the code, but somebody wrote it. So.
Yeah, I'll definitely check that out. Thank you very much. And I'm sorry for everybody else, I keep forgetting to repeat the questions for the listeners. The point was made that Alex Stepanov may actually have implemented a similar data structure in the past that I could use as an example here. But cool. Any other comments, questions, or concerns? All right. Yeah, so we said all this, blah, blah, blah. Yeah, and so then we move through a temporary if we have overlapping pointers. I actually also wonder if the way that I'm detecting overlap here is technically UB as well, because I have to do pointer arithmetic with things that aren't actually arrays. I'm not 100% sure about that one. But yeah, if it would overlap, we
Have you
move
run
through.
through the UBSAN?
So UBSAN does not complain about that. But that's one of those things that comes down to like pointer provenance. Like I don't think UBSAN would complain about it. But then, yeah, erase also has similar challenges, but it operates in reverse. We don't have to worry about erase overflowing the vector, but it still has to deal with these same problems of shifting objects by less than their size.
Or you could just leave displace blank.
So that is one thing that we've considered. I've talked about, so I've given this talk a couple different times in different contexts and people have suggested that. The main thing that I'm afraid about there is just that then you have to start worrying about fragmentation, but it is definitely doable. And actually last night I was considering a whole thing where like, if you keep some storage on the side about like where are your holes, like you might be able to get something like that done. I haven't totally fully explored that idea yet, but that is definitely a possibility. That does, of course, mean that potentially over time you'll use more memory. Like what happens if the next thing you try to push in is not small enough for that hole? Does that mean that you have to start actually storing things out of order?
Assuming you know the ratio of blank, right? You could like trigger it, same way a vector triggers a reallocation.
Yeah, that's true. And then like compactify during reallocate. That's actually, I actually like that. Yeah, like compactify next time you have to reallocate. That's also a cool idea. Yeah. Yeah, definitely we'll consider that. But cool. Awesome. So then, yeah, those are the challenges of mixed alignments. So back to implications of design. Member functions like insert and erase come with unique challenges for this data structure. Mixed alignment can lead to complex interactions. When I was starting out with this whole thing, I definitely did not foresee this overlap issue. There was just this point where when I actually went to write the insert function, there was a certain point where I was like, oh no, like I never considered this. But yeah, so it can lead to complex interactions. Are there any other implications? And there was, the next thing that we're about to talk about was hinted at earlier in this talk. Cool. So I'm calling this next section the woes of the subscript operator. So there are challenges that come from this for the subscript operator as well. So in addition to the subtleties around insertion, there are also complications for our access APIs. So yeah, design minimizes memory quite nicely, but it has unfortunate implications for the subscript operator. So consider the following code. So this is again just using std vector and std variant. It's the one we've been using this whole time with just the boolean, double, and string. We put the same values in here, but then on line 2 here, we actually reassign to index 3 the 4th element. So it goes from 3 to 1 plus 2. We then actually print this out, and we can see that the value updates. Like hopefully this is not surprising to anyone. This is what we would expect this code to do. But let's talk about like how does this assignment actually work? So I'm talking about the assignment on line 2 here. Like what does this actually do? So we first call the subscript operator of std vector. That returns an L value reference to the requested index of type std variant ref. We now are assigning to a variant reference. And so next we call the assignment operator of std variant. That internally does some template magic to figure out like what is my runtime type, what operator do I need to call, and it ultimately ends up deciding to call the assignment operator of std string. The assignment operator of std string then receives the string literal and internally does whatever it needs to change its value, causing the print statement to see the new value when we actually run that. And so this is how it works in the typical case here. But what happens if we try the same thing with our vector? What does it actually do? Hopefully the same thing, right? But what we actually see here, so we have our vector here, same thing. We're just now using our VV vector. We assign to this, it doesn't throw. It compiles and doesn't throw. And then at runtime, you can see we get the old value. And so what is going on here? Like this is very, very unfortunate. And I've not been able to come up to it with a clean solution to it yet. So the value doesn't update. What's the problem here? Well, so the issue here lies in the first bullet point of our assignment explanation. The subscript operator of std vector returns an L value reference. Like the problem here, and there's probably many people in the audience that have figured this out, the problem here is that like vector is actually storing a variant. And so it can give a reference back to that variant that we then assign through. The problem is that we aren't storing an actual variant. Like that's literally the whole point of the data structure is that we're not actually storing a variant. And so the problem is that like we don't have an L value reference that we can return. Yes.
So here you will have to wait for cpplusplus23, but you have the start lifetime. It actually copies it to what you want it to be. Right now you can do it by yourself, but basically with the 3 you will get it from the standard.
Well, I mean, so I guess what I'm wondering on that one, that doesn't really solve us, that doesn't really help with the problem of operator, the subscript operator, right? Like
you will have to do it by hand, but you can start lifetime, you can create an object that you will hold, and then return a value. L value.
Well, so what I'm wondering about there, like, where does the L value actually, like, where does the actual storage go? Like, inside the actual vector class itself?
No, inside the class, but you will have some temporary storage that you will get. But the problem is that you will never know when you can delete it.
Well, exactly. So I was going to say, I actually had implemented a similar kind of thing before that was returning a value from its subscript operator. And you can do that where you like cache an instance in the class essentially, and then you return that as the L value. The person assigns to that. The problem is that then at some point you have to sync that back to the actual storage that you have, and it gets kind of confusing as to when to do that.
Because, and this is just a talk that I have right now, because you're not using stud variant. You're using my variant.
But in this case, I'm actually using no variant at all.
Oh,
Yeah.
but here, if you want to return an L value, you have to return an L value of something. So let's say you are returning an L value of your kind of variant, and the destruction of that kind of variant is just removing the memory from your system. So you can just push it out to the user. He will use it. It will go out of scope.
Okay. Yeah, it's so one thing that I was hoping to get out of this was using standard variant, just because I'm kind of hoping to be able to use standard visit and like all of those basic functions. That is an interesting idea, though.
For standard variant, you can still do it. For example, you will not return standard variant. You will return a unique pointer to the standard variant, and then the deleter of the unique pointer will free the memory from your system.
Yeah, I mean, I guess the main thing that I'm thinking about here is just still actually getting like the reference to the like the assignment to the reference to actually work properly. Like it's
if you will take it and you will copy the data to your new buffer and it will start its lifetime, it's what you want it to be. Then yes.
Okay. Maybe we should talk more about that offline. I'm kind of curious. Yeah, so we're not actually storing a variant. Maybe there's something clever we could do there. But the way that this works right now is that upon access, our vector creates a temporary variant to return, which does get assigned to, but it then evaporates at the end of the line. And so like this here implicitly creates a variant instance that then gets assigned to, and it's just poof at the semicolon, it goes away.
If you could, but well, just an idea. If you go back to the piece of code. All right. If you could somehow have that return something where it would directly assign to your internal type,
yes,
as opposed to having to go through that variant.
Yeah. So that is something that I've considered here. So the statement here essentially was that we could use a proxy class. So that is something that I considered. So basically, the idea here is that, as Pete was saying, the idea here is don't have this return a vector. Don't have this return a variant. Have this return an object that is implicitly convertible to variant. So like if the user had stood variant here and pulled this out, that would just implicitly decay to the right type. But what's nice is that with that proxy type, you can override its assignment operator. And then like basically when you construct that thing, it caches a pointer to the vector it was created from. And then when it's assigned to, it would actually call the function on the vector to make sure that actually gets updated in place. You could do this. I've chosen not to do this because I kind of think this is an anti-pattern, to be honest. Like this is actually how vector bool works. Yeah, exactly. And if people are not familiar, vector bool is like famously hated in the standard because it doesn't really work very well. So like if we return a proxy class, like it works it works in two cases where the user declares a variant statically and it decays to the right type, or if you're assigning to it. The problem is that the second that the user writes auto, like you've now leaked a proxy class into the user's program. Yes.
What's the problem with vector bool?
Oh, I mean, basically this, like it breaks people's expectations. Like if you don't return the type, like it returns, my understanding is that it returns a proxy type because it is allowed to store the bools in the vector as bit fields essentially, and you can't form a reference to a bit field. So for its assignment operator, I believe it also uses a proxy class to be able to actually get the assignment to work properly. And the real issue is generic code. Like in C++03, when this was added, you didn't have auto, and so it was slightly less problematic. But say that you you use the subscript and pass it into a template function. Like it's not going to decay to variant. It's going to stay as the proxy class. And then when you try to do variant things with it, it may end up blowing up. And so like this approach can be kind of hostile to generic code. That's why I've chosen not to do it. Another question.
It's actually worse than that because suddenly operator bracket is order n. Because you have to insert.
Oh, yes.
So you cannot implement immutable element access.
It becomes order n if you allow. So if you assign to it from a different type, yes, then you run back into the insertion case and you have to start reallocating. That is true. Yeah. If you assign the same type of thing, that shouldn't require realigning the storage. But yes, you are right. If you change the type, that would require that. Yeah.
And if not, if you don't, get worried about that case, you can. I think the natural thing would be to return some kind of variant of references.
You could try that. Yeah, like maybe have like stood ref or something inside of the variant. You could try that. That's a clever idea. So really what it comes down to here is just the more that I was brainstorming about this, the more that it felt like I was trying to fit a square peg into a round hole. And so that's why I just kind of decided, like, let's just be honest about the characteristics of this data structure. Like, read-only access works for the subscript operator, but you can't assign to it and have it do reasonable things. The thing that I'm really sad about is that I can't make this a compile error. Because, like, last time that I was doing something like this, I was in control of both of the types. And so I could just delete the R value overload for the assignment operator, but I don't own variant, so I can't do that. So I can't even make this a compile error, unfortunately. But yeah. But so getting back to where we were going here, to work around this, the approach that I've taken is that we need some new APIs. So unfortunately, this does compromise our hope of being able to get a drop-in replacement for vector. But what I have here, if people are familiar with standard get, the idea is that we have a .get member function. It works the same way where you tell it what type you expect to get. I am actually storing an int I am actually properly storing an int, so I can return an L value reference here. Same for the string. These work as you would expect. I also have a .visit here, which is similar to standard visit. The difference here is that, like, this allows you to do the same thing but without knowing what actual type is stored. And you can see that I'm taking this by L value reference here. And so at the moment right now, I am just printing this, but if you assigned back to this val, it would actually update inside of the data structure. So I do have APIs that allow for in-place mutation, but unfortunately, I do think that without choosing solutions that I think are kind of compromised, I don't think that there really is a good resolution to this. I think this is just a fundamental conflict between the API versus the optimization. So yeah, the .get and .visit APIs model there's STL equivalents. You can also add a .replace because there's the question of, like, so in this case here, I can assign an int to this, but this is going to be an L value integer reference. So like if I do like 2.0 here, it's going to get converted into an integer. And so if you want to actually change the type that's stored at a particular index, you can add a replace function. But the problem is that replace ends up basically just being a special case of insert because you may end up having to realign the data structure again. But that can handle changing types. And the subscript operator does still work as expected for read-only interaction. So like this still does what you expect, which is why I haven't, like, when I first came across this, I was like, should I even have a subscript operator? And I was like, how do you call it a vector if it doesn't have a subscript operator? So this does still work, but you can't assign to it, unfortunately.
So Deck2 returns a copy there, right?
It does return a copy, yes. So I originally had slides here about handling move-only types because the problem here is that this has to copy. And so how do you put move-only types in this vector? I ended up deciding that I probably didn't have enough time for that in this talk. We can come back to it at the end if we want to. There are some things that you can do to try to work with move-only types. But yeah, so for implications of design, we talked about all of these. Not storing actual variance in the vector leads to difficulties for the subscript operator. And I think this one is just a fundamental conflict, unfortunately. Yes?
I just want to add a small thing. The copying, most of the modern compilers, they understand the pattern of copying into in the lifetime and copying outside in the lifetime. So they removed it. They mostly optimize it out. I'm saying again, mostly. Mostly, yeah. Mostly it will be the same as moving an object, but not always.
Okay. Yeah, well, and actually, so we're about to get into benchmarks, and I did end up seeing this is actually less expensive than I thought. So that might be coming back to what you're talking about. But cool. Awesome. So benchmarks, like I was saying. At this point now, we've talked about the whole design here, the implementation. We've talked about some of the problems that come out of this and some of the difficulties that you run into with this data structure. But so let's talk about how does this thing actually perform. I remember somebody actually suggested I change the color of these. I probably should have, but oh well. So what are we looking at here? So this is specifically benchmarking the benchmarking the timing of the subscript operator. So the blue one here is static vector. So I have a static vector implemented in my library. The red one is dynamic vector, and the yellow one is standard vector. And so the y-axis here is time in nanoseconds, and down here we have a bunch of different cases. So we have accessing a Boolean, accessing an integer, accessing a float, accessing an SSO string, and then accessing a long string that is not going to be a small string optimization. And what we end up finding here is that for all of the trivial types for the subscript operator, the performance is like roughly order of in all cases. Like there is a little bit of overhead here, but it's not too bad. Where we really start to see the overhead here is when we have a string that actually allocates and like has data on the heap. Using the subscript operator, we have to copy out, which means we have to reallocate. And so that's why in this case here, it ends up being about twice as expensive as standard vector, because we have to reallocate in this case. The good news is that we do have in-place mutation APIs. And so we don't necessarily, we have to do the copy out when we use the subscript operator because of everything we talked about. But we don't have to do it in the in-place mutation case. So in this case here, I've called this like standard get timing. The idea here is that with the standard vector, we're calling standard get on the variant. For my vectors here, we're just calling .get, and it's returning that L value reference. And so with the bool, integer, and float. So the thing is that what's interesting here is that we are still seeing significant overhead for the dynamic vector case. So now, like, notice the scale here. Like, vector does this in half a nanosecond, and my code does this in 1.5 nanoseconds. So like, it's still kind of order of, but it is larger. My estimation for where these spikes come from are largely come down to that virtual interface. Like, we have to go through a vtable to actually access the offsets themselves to be able to figure out where the stuff is located. So I imagine that's where this overhead is coming from. But I cannot explain why vector does so badly in these cases. I don't know why. This was benchmarked on this laptop here. So this was using like libc++ and like Apple Clang. So I don't know if there's something weird going on with vector here, but this was reliably reproducible. I don't know why standard vector is so slow on these cases. Yes?
I have seen similar weird behavior with the Apple.
Oh, really? Okay. Yeah. I should try running the benchmarks on like Linux and GCC or something and see what I get. Because yeah, these don't make any sense to me. Like, I think that my data structure should always be slower than vector, but yeah. And one thing that's also interesting over here, so you can see the fact that my static vector in many cases is faster than standard vector. This, I think, is the compiler making a fool of me. I think what's actually going on here is that in the static vector case, the compiler can see literally everything. It can see the inputs. It's a static type. It doesn't have to allocate. And so I imagine in this case here, the compiler is probably literally just optimizing out the entire thing and just like returning the answer. So I think that these are probably not real results for the static vector specifically, but cool. Any other questions on this? All right. And so then I also have timing for pushback and popback. So the idea here is that, so this is for a Boolean, an int, a float, and a string. The idea is we literally push it in and we pop it immediately. And we just check and see what is the timing for this. So this is one where we don't really take significant overhead versus vector in any case. So this one is, this one worked pretty nicely. And now getting into the more interesting benchmark. So this one is actually on memory usage. So specifically what this is, I don't have static vector on this slide because it would be kind of pointless. It always uses the same amount of memory. But what I'm doing here, so this is using the same vector that we've been talking about for most of the talk. So it's that bool int double stood string. And this one here is specifically just pushing in ints. So in that case here where we're just pushing in integers, it's not the smallest type, it's kind of in the middle. We end up getting something like 60% memory savings versus the actual standard equivalent. So that is pretty cool. On the slide here, I have 1,000, 11,000, and 111,000 pushbacks. In actual fact, I generalized this out to 11 million. I just don't actually have that on the slide here because it makes all of the rest of this unreadable. But this trend does continue at least out to 11 million pushbacks. And then this next one that we're considering here, so this is the same vector again. It's that same set of types. But instead of pushing integers, we are now pushing random types. And so like literally I'm using like the stood random engine or whatever in the random header. I have some prototype objects and we're just spinning over those and just randomly pushing objects into the vector. And even in the case where the objects are pushed totally randomly, we still have around 40 to 50% savings. So even in the case that is probably the least complementary to this data structure, we do still see meaningful improvements. So that is cool to see. And I also generalized this out to 11 million. I don't have it on the slide because it makes it unreadable, but this trend does continue up to 11 million pushbacks. But cool. So it looks like we actually will have time to get to the lessons learned. So if anybody has any questions, otherwise we can get into the bonus material. Oh, yes, question.
So have you considered, so like one of your early designs considered was to have everything heap allocated.
Mm-hmm.
What about a heap allocated variant with SSO.
So actually, I was actually talking to somebody at lunch yesterday that suggested this idea, and I really want to try seeing where that goes. Because so the question for the audience is, what if we take a variant that actually has something equivalent to a small string optimization? And so the idea is that we provide some static storage inside of the vector. If the object is small enough, the vector can store it in situ. If not, it falls back to heap allocation. That is a really interesting idea. I'd like to see where that goes. It's one of those things where, like, one thing that's nice about this is that the behavior is guaranteed. With that one, it kind of comes down to a question of how big do you make the small object storage? Like, what's the use case? It could be that you have a vector that always pushes stuff in that's bigger than the small storage optimization, in which case it's no longer an optimization. But it is a really interesting idea because it avoids some of the other problems here, like the aliasing problems during inserts. But yeah.
Actually, I was thinking more stood vector of your non-stood variant, which then also has like your trade-offs in terms of all your design implications that are
right,
like tricky for users. In terms of the API.
Yeah, and I think that would be workable. It's just, again, the question of, and I guess in that case, then maybe the user explicitly parameterizes the variant, and so they can be aware of what their storage requirements are. That could be another way to try to approach the problem. It would be interesting to try to prove that out. But yeah, thank you. Yeah. Any other comments, questions, concerns? Cool. All right. So lessons learned. So this was the first time that I was writing non-trivial code in C++20. It was very cool to have the opportunity to do this and provided many opportunities for learning new things. So the first one here, this was actually mentioned extensively in Jonathan's talk. I would really recommend that you check it out. It was actually really awesome. But yeah, implicit lifetime types in C++20 can actually make C-style type punning well-defined in some cases, which is actually really interesting because it never used to be. And another one that I bumped into by mistake here is that stood bitcast can discard const. And what I mean by that, it actually, like, I don't think it's a bug with bitcast. I just didn't expect it to do it. But if you ask bitcast to cast from t const star to t star, it will totally do it and has no complaints about it. The way that I ended up discovering this was that I wanted to build this on GCC 10, which has a partial STL implementation, and it doesn't have bitcast. And so I changed those over to a reinterpret cast, and suddenly everything blew up because I was accidentally discarding const. So that is, you got to watch out for that one. The next one here was really bizarre, and I don't know if this is something that's generally true, but for this data structure at least, I ran into the case where adding a single throw statement led to a very significant degradation in performance. And it was not a throw statement that fired. It was just the fact that the throw statement was in the code caused the compiler to less aggressively optimize, which was very surprising. Question?
Where did you put the exceptions?
Well, we will get to that. So yeah, I have a slide for it. And so then the last one that I have here is that seemingly innocuous optimizations can bubble up to interface impacting changes. That is definitely, I think, a lesson from this data structure. And so the first one that I have here is that memcopy is magic, starting in C++20. There are other things that are magic too. Memmove is also magic, but C++20 defines what it calls implicit lifetime types. And so the interesting thing here, like, it used to be the case that if you are working with like network code and you're getting like the bytes of a serialized struct over the network and then you try to work with it, there was no real good way to do that without UB. But at this point now, memcopy is actually specified such that it will implicitly begin the lifetime of 0 or more implicit lifetime objects, if doing so would result in the program having defined behavior, which is just, I love this wording. Like, this is directly from the standard. Like, the standard's just like if we can fix it with memcopy, we'll do that, but otherwise we don't fix it. Like, it's still UB if memcopy can't fix it, but if it can, it will. And the thing that's kind of entertaining here is that the types that memcopy is supposedly initializing here are like entirely notional. Like, memcopy is not a template function. It has no idea what it's supposed to be initializing. But the standard just says it just initializes however many of whatever it needs to make your program well-defined, which is like pretty awesome. I had a good time laughing about this. And aggregates of implicit lifetime types are also implicit lifetime types. And so this composes in the way that you would expect. And I thought you had a question. Okay, cool. All right, so then the next one, so this is getting to what I was talking about before, the hidden cost of exceptions. So in C++, exceptions are expected to be 0 cost on the non-throwing path. It has always been my observation that this is true. You don't pay for what you don't use. But even though they may not come with a runtime cost, the presence of exceptions in code can cause some compilers to optimize less aggressively. And so the specific example that I ran into here was this. So let's take this code here. So this is a static vector in my class. So basically we're saying this static vector is going to have 64 bytes of storage. We're only going to store 16 things in it. And at the moment right now, I'm saying we're only going to put ints in it. And so this just pushes back a call to rand, and it then just immediately grabs that same index. So like, there's obviously not very much going on here. It's very obvious to a human that this data structure does not do anything useful. But like, there's still all of that machinery underneath this that we've been talking about for this whole time. Like it doesn't look like much code, but there's a lot of code underneath this. And if we actually compile this with O3, what we end up getting is this, which is just so awesome. Like, you know, whenever people ask me, like, why do you bother with C++, this crazy complicated language? This is why. Because like, this is just amazing. I was so happy when I saw this. But so let's take another case here. So same exact code from this perspective. The only difference is, so inside of this static vector here, this is actually an API adapter on top of a lower level class. Static vector, this is actually, a static vector and dynamic vector are actually served by the same wrapping API adapter. And so it's actually really useful if I can assume that the lower level types all have the same functions. And so even though a static vector cannot resize, it still has a resize function. The original version of my implementation of this here just asserts false and then returns null pointer so that if you have assertions disabled, you'll probably immediately crash and push back. But the idea here is that this function exists so that it makes the template logic easier, but it's a logical error to call this function. And so this was, if you call this function, it means you necessarily overflow to static vector. And so this is the original version of this code, which led to this jump rand. And so like, you know, inside of pushback, there's potentially a call to resize if the stuff is not, if you don't have enough space. But this code does not get called. But then I was like, you know, like this is kind of gnarly, like putting an assertion in the user's code, like that's not super great. Let's try to throw bad alloc because like that's more indicative of what we're actually doing here. The problem is that literally just changing this one line that does not execute results in this, where suddenly like the optimization falls apart and it like totally falls back to the default case, which is kind of unfortunate. I don't know if there's really lessons to be taken from this, but this is something that I did not expect to see that was very surprising to me. And so this is actually the version that I kept just because the performance, I thought it was, you know, kind of sad. So this behavior is present in GCC 10, 11, and 12. It is fixed in 13 and on. The issue also presents in MSVC, although to a lesser extent. MSVC doesn't do quite as well at optimizing in the first place. And so like it's not as big of a hit, but it does also happen in MSVC. And all versions of Clang that I tested seem to be immune to this issue. So that is kind of cool. But yeah, so wrapping up, just kind of talking about our final design here. We retain a contiguous storage array supported by metadata to track offsets and types. We bit pack all the things. We deal with mixed bit alignment gracefully. We provide alternative APIs for the subscript operator to work around fundamental design implications. Yeah, the data structure presented in this talk is a simplified version of the actual data structure. It leaves many things unhandled, such as what do we do with handling types with throwing move constructors? Those are really nasty. How do we make iteration work? What's our dynamic growth strategy? This one's actually particularly interesting because again, we don't know what's going to get pushed into the vector next. And making that one work is kind of interesting. Exception safety guarantees, and I should have put move only types on this slide because I originally had a slide for that and I pulled it out. But so we also didn't talk about move only types. But yeah, this one is actually the end for real. So thank you very much. Yeah, looks like we had another question. Mm-hmm.
Just maybe two things. One thing is static vector is static thing. Constant expression functions don't allow undefined behavior. Maybe you should look at that.
Oh, that's like to see whether or not I have problems with like the insert case and stuff like that.
Not only just for resize. If you try to do something that is undefined,
I see what you mean. You'll get a compile error then if you try to overflow it. That's a good idea. I like that.
And the other thing is, have you tried to use expected instead of throwing exceptions?
I have not tried that yet. That would be interesting to see where that goes because I would expect that that would perform better. Yeah, I guess we'll see. The weird thing about that then is that like, how do I surface that all the way up to the user? Because the way that this is the context in which resize is called is pushback. And so like pushback returns void. Like, have pushback, return an expected, or like an error type or something like that. Like, yeah, but that is an interesting idea. Thank you. And the other statement here was that in the static vector case here, since I was talking about the fact that this could easily become a const expert data structure, if we do go in that direction, this actually potentially gives us an escape hatch to make it less likely that users will overflow this vector, because then if it's const expert, it potentially becomes a compile time error if they do. But another question.
For your bookkeeping, you use a pair of arrays. Have
Yes.
you consider using an array of pairs?
I'd like merge them together into one.
Yes.
I had thought about doing that. The only reason that I didn't is just because it is so specifically for the bitmap itself, it's easier to do that if it's just contiguous by itself. Like if I have to do a thing of pairs, like, I mean, I guess that would mean that I would have to always be a minimum of at least 1 byte for the type information. I don't know how I would get around that. But I could do that. Maybe it keeps the data a little bit packed together nicely, and maybe it's more, we get better cache locality. But yeah, the reason that I chose not to do that was because I wanted to actually use a bitmap for the type storage. But yeah. And sorry, the question was, instead of having 2 different storage arrays for the offsets and the metadata, can we combine these into one array of pairs, essentially? Another question.
Have you considered, instead of dealing with mixed alignment, using the same alignment for all types?
Using the same alignment for
all the types by just overlaying the rules and stuff.
You could do that. I have not gone, so like the main thing that I've been chasing with this data structure is minimum possible memory usage. And my fear is if you give everything the same alignment, you're going to end up with a lot more padding bytes.
Depends on the order.
Yeah, it very much depends on how you push. But I'm afraid that in the generic case, it's going to end up using more memory. But that is a good way to go about it, because that completely resolves the issue with overlapping pointers. Another question.
Yeah. So I often have code where I use a strict vector, but I don't actually want to index. I just want to store data and then iterate over it. And with like a vector variant, in that case, like you can simplify it a lot. You don't need the offsets, etc.
Right. That's interesting. What do you actually, like, you just use it to keep objects alive, essentially?
Yeah,
Or
I need to store some data to iterate over it later.
Okay, yeah, that's interesting. So
How
the
do you
state,
reform your objects? Then? It's just
a good question. Yeah.
But I mean, you still store the types, but you don't store the offsets, because based on the type, you can figure out the next offset.
Yeah, you could do that. If you walked the whole vector, you could figure out what the next offset would have to be. Yeah. So the statement there is that there are use cases for vector just to keep objects alive where you actually don't need a subscript operator. So I could maybe simplify parts of this design. The other question was, I could also just say that everything has the alignment of the maximum type so that I don't have to worry about a lot of this other stuff. But yeah. Any other thoughts from anybody? Another question.
So in my experience, this idea of having types that can substitute other types, or especially data structures that can substitute other data structures, is problematic, because you end up with APIs that are not true to the data structure, to the physics of the data structure. And I think it's more useful to actually have APIs that respect the limits of the data structure with respect to complexity and all that, but instead of concentrating on the equivalence, concentrating in the fact that you can go round trip between the 2 types, two data structures. So it looks like your data structure is very good for storage. So make it such that you can, with iteration and copy and standard algorithm, go from vector of variance to your vector or tape, whatever, and then back.
Yes. Okay.
That's
that
would be, I think that should be what the work should be concentrated on.
Definitely. Yeah. So the statement was, so we have a vector here that tries to model vector, but is not able to fully model all of the functions correctly. And so one way that we could try to ease this transition is making sure that it's very easy to interoperably convert between the two, potentially using standard algorithms or like conversion operators or something like that. Exactly. But definitely, yeah, it's a good idea. And I think I saw you had your hand up as well.
Yeah, just for this case, would varying resize to be private be sufficient for this?
Oh, well, so you mean like for this case here?
For static.
Yeah, well, so the reason that I allow these separately is just because, again, you could have any number of things here. And so, like, if you say I want 16 things, it's not clear to me how many bytes do I actually need to allocate for that. Because I could just take the largest, T and multiply it, but we're then back in the same case as vector.
Or sorry, I mean for the member function resize. You don't just to
make it private so you can't get to it.
Yeah, you could do that. So the where resize is actually declared. So resize is not declared on this object. So this is an API adapter that works on top of an internal class. So resize is on. It's not declared private, but it's in like a detail namespace. Like I would say that the type itself is private. But yeah. And the point there was just making sure that the resize function is private so that nobody can call it. But yeah. Cool. Oh, and question from David.
Is there like an open source implementation of this?
So I really wish there was. Unfortunately, I've not completed the open sourcing process with Bloomberg yet. And that's actually also the reason that I can't give you a compiler explorer link for this, because I wasn't able to minimize this down to like a minimal case. So the way that I reproduce this in compiler explorer is by using the full source of my library. So it will be open source one day. It is not currently open source, but it will be. Yeah. Cool. Yes.
Just maybe something that will be very unpopular. Have you tried to go a little bit more unsafe and to use unions instead?
I have not. That's an interesting idea. It's yeah, it would be a fun direction to prototype in, but not so far. No, unions can be awesome if you need absolute minimum memory usage, and that sounds useful for this. But yeah, thus far I've been trying to stay within safe APIs. But it's a good question. The question was whether or not I have tried prototyping out using unions instead of variants, and I have not yet. But yeah, cool. Any other comments, questions, or concerns from anyone? Another question.
So it's about the alignment. So just hand waving here. I heard things that I heard. So x86, there is no penalty, nothing. It just works.
Quote unquote. Yeah.
Exactly. But apparently, older x86 would have either a performance penalty or would crash.
Oh, really?
But
okay.
Even modern x86, when you start mixing that with SSE or SIMD, then you need the alignment.
I have heard that before.
It might crash.
Yeah, like the SIMD registers can't handle the unaligned accesses. Yeah. Well, and I think that, so I could be totally wrong about this. It could be that, I guess like modern CPUs fetch whole cache lines, so it's probably less of a problem here where you have an unaligned read. I was still thinking that the CPU had to issue 2 separate reads and fix it up. If you did that, it just does it for you automatically. So the main thing that I'm aware of with x86 where that becomes a problem is in threading concerns. Like normally, like an aligned quad word read would be atomic, but like if you do a quad word read on a misaligned address, it'll have to like do 2 separate reads and you can get torn reads. So that's another problem as well. But cool. Any other comments, questions, or concerns? Awesome. Thanks so much, guys. And